Hey guys, welcome back. We are looking at YOLO object detection series. As part of it, we saw the first two versions of YOLO, YOLO version 1 and YOLO version 2. In this video, we will discuss about YOLO version 3. YOLO version 2 was the most accurate and also the fastest object detector when it was released 2 years back. But 2 years down the lane, it's no longer the most accurate one. It is still the fastest object detector, but the accuracy wise, it is not the state of the art. There are other models that came up like SST and RetinaNet, which are the state-of-the-art object detectors in terms of accuracy. But YOLO is still one of the fastest model. So authors have made some modifications to YOLO-V2 and released YOLO version 3 in 2018. As stated here, it is only an incremental improvement. On a higher level, it has a better feature extractor or backbone, which is called DarkNet-53, and it has shortcut connections, residual blocks, as well as leaky ReLU. So they have actually combined various techniques from the previous papers. Let's dive into it for more detailed understanding. Let us start with the backbone or feature extractor. In YOLO version 2, DarkNet-19 was introduced. It is the fastest and accurate model for classification on the ImageNet dataset. This was used as a feature extractor for YOLO version 2. All are plain convolution and max pooling layers. With this network, YOLO V2 struggled with small object detections. In order to detect smaller objects, we need better fine-grained features. So this network doesn't have any kind of skip connections or residual blocks, which will keep the fine-grained features. So small object detection is not feasible with this architecture. YOLO V3 incorporates all these features and introduced a new backbone called DarkNet-53. The number 53 indicates the number of layers in the classification network. So if you observe here, there are 53 layers here in this. If you observe the architecture, all the layers are either 3x3 convolutions or 1x1 convolutions. There are no pooling layers in this anymore. And you can see that there are residual blocks. This is how a residual block looks like. So it has this kind of skip connection in between. And also each convolution block here, it is actually a combination of convolution layer, batch normalization and a leaky ReLU. So these are all the changes they have made with respect to the architecture. Now with the help of these residual blocks, and also the leaky ReLU activations, it is performing better than DarkNet-19. If you observe the ImageNet results, DarkNet-53 is almost as accurate as ResNet-152 and it is better than ResNet-101. But if you observe the speed, it is actually much faster. So this is actually used as a feature extractor for YOLO version 3. DarkNet-53 is only used as a feature extractor or backbone, but we need additional layers for doing the object detection. Let us take a look at the whole architecture. This is how the whole architecture of YOLO V3 looks like. Initially, all these layers you can consider as backbone layers till layer number 53. After that, you have some more layers in between, and there are upscaling layers and there are convolution layers, 1x1 convolutions. All of them are stacked together accordingly. So we'll come to this in detail later, how these predictions are happening at different levels. But for now, you can check that this is the total architecture of YOLO V3. There are no fully connected layers. Everything is convolution layer here. Even the predictions are convolution layers. There are no FC layers. Now, as we mentioned earlier, each convolution layer has a batch normalization and a leaky ReLU layer. Also, there are no pooling layers in the whole architecture. Now, how can we downsample from the original image to these dimensions, smaller dimensions, without any pooling layer? Usually pooling layers are used for downsampling the image. So instead of using the pooling layer, they used the convolution layers with straight 2. This prevents the loss of information. If you check the difference between the convolution and pooling layer, if you observe this is the max pooling. In max pooling, you consider this particular grid. In this grid, you take only the maximum element as the output. That is what 5 here. What about the remaining things? These are ignored. Same way for this particular block, only 9 is considered. The remaining things are ignored. Right? So this actually has loss of information. Now instead of that, if we use convolution layer, the first point is the filter which is visible here. These are actually learned features. That is one thing. So it will actually learn out of these 3x3 block, which are more important features it will learn and it will take accordingly. That is one thing. And if you use straight 2 here, the next block will be like this. So automatically instead of 3x3, you will get 2x2 filter here output. So this example is for a 3x3 with a stride 1, but usually if you use stride 2, you will skip one block in between. So your output will be 2x2. So instead of using max pooling layer for downscaling, we can use convolution layer with the stride 2 to reduce the dimensions. Both are achieving the same result. In pooling layer, we are having loss of information, but convolution, we don't have that loss of information. And along with that, if you observe till here, it is actually downscaling, and after that, it is again scaling up. So these are called upsampling layers. You can see here, these are upsampling layers. These upsampling layers and these kind of skip connections, these actually preserve the fine-grained features. Now, because of these features, you can detect the smaller objects as well. Now we will see in detail how these predictions are happening at 3 different places. Similar to previous YOLO versions, YOLO-V3 also follows the grid-based approach. So it divides the whole image into number of grids, and each grid is responsible for detecting a particular object. And if you look at YOLO version 2, they have introduced anchor boxes. But YOLO version 2 has actually 5 anchors. Instead of that, in YOLO version 3, they have reduced that to 3 anchors. So each grid cell, you have actually 3 anchors. If you see the example here, for this particular grid cell, there are 3 anchor boxes. These are sample anchor boxes, only for representation purpose. Now, if we see each grid cell, what are the predictions it will take, it is almost same as your previous YOLO-V2. So each grid cell actually predicts the bounding box coordinates, the class confidence scores, along with the objectness score. These 3 values it will actually predict. So these are the actual predictions. So if you see, this is the prediction per each grid cell. So now each grid cell has 3 anchor boxes, right? Anchor 0, anchor 1 and anchor 2. So for 3 boxes, for each and every box, you have offset values which are XY coordinates and scales which are width and height. So these 4 values include the bounding box value, and along with that there is an objectness score. Along with that, these are the class probabilities. So class probabilities number actually depends on your number of classes. So if I have Pascal VOC, then I have 20 values here for class probabilities. If I have trained on Coco, then I have 80 values here. So basically YOLO version 3 has been trained on Coco dataset. So these probabilities are 80 values. So if you observe total how many values we will get, 85 values we are getting for each anchor box. And we have 3 anchors. So in total we are getting 85 into 3, which is actually 255. Okay. So these are the total number of predictions we are getting. So this is the example for Coco dataset. If you see, these 3 are actually for 3 anchor boxes. The first 4 values are bounding box coordinates, and next one is objectness score, and these are actually class probabilities. There are 80 values because Coco dataset has 80 classes, 80 categories. And if you see, for each coordinate, each bounding box, you have these parameters. And here the example is actually 13 by 13. So you have 13 by 13 grid cells. So per each grid cell, you have these many predictions, and there are 13 by 13 grid cells. So this is how the prediction vector looks like actually. And we have seen previously that the predictions are happening at 3 different places. So let us see that. So if you observe this, the predictions are happening at 3 different places in the network. We know that the image is getting downsampled by the time it reached here, right? Now here the predictions are happening at this particular layer, which is actually layer number 82. And after that, the features are actually getting upsampled here. And then the previous features are again getting concatenated here through skip connections. And after that, again at 94, layer number 94, you are having another predictions. As the features are upscaled here, the scale will be higher compared to this one. So here it is a small scale, and here the scale is much bigger. And after this part, again the upscaling is happening here, and comparatively whatever the scale we got it here at the end of upscaling, the similar scale whatever we got in the previous connections, we take that information through the skip connection and we concatenate here. So these concatenations are actually for getting better features. So now after you got one scale, again you add couple of convolution layers, and again you take one more features at actually 106. So the predictions are happening at layer number 82, 94 and 106. 3 layers at 3 different scales. So if you observe here, the image is getting reduced to a particular scale. So here if you see the term called stride. So stride, what do you mean by stride? Stride is basically how much an input is getting downscaled by the time it reached this layer. So by the time it reached 82, layer number 82, the input image has been downscaled by 32 times. That means if my input image is 416 by 416, it has reduced by 32 times by the time it reached this layer. That means what will be my feature vector size here? It is actually 13 by 13, because if you take 416 by 32, you will get 13. So this is the feature vector size I am getting here. In the similar way, we are actually upscaling here, right? So from 13 by 13, that means from this layer only 13 by 13 is getting propagated here. So 13 by 13 is actually upscaling to double the dimension, which is 26 by 26. If you check here, stride number 16, that means 416 divided by 16, which will give me 26. So here the feature vector size is actually 26 by 26. And similarly, this 26 by 26 here is getting again upscaled into 52 by 52. So that is why stride is 8. So 416 divided by 8 will give me 52. So these feature dimensions are actually 52 by 52. So to detect the objects at different scales, we are actually predicting at different scales. This feature vector is only 13 by 13. This feature vector is 26 by 26. This feature vector is 52 by 52. 13 by 13 feature vector will give me bigger objects, and 52 by 52, this is a bigger feature vector. So even if the object is a bit smaller object here also, it should be able to identify here. And this is actually medium scale, right? For identifying the predictions across different scales, small objects, bigger objects and medium objects, we are taking the predictions at 3 different locations at different scale levels. So this is what it is happening here. It is the same example, just in a different illustration. So if you see S by S, that is actually 13 by 13. If you take like this, then it is 2 times S, which is 26 by 26. Then it is 4 times S, which is 52 by 52. This is how it happens. And at every stage, for every grid cell, you have these 4 values: objectness score and class confidences. This is again the same information in just a different representation. These bigger boxes and smaller boxes, these dimensions actually indicates the scale. If you see, these are 13, 13, 26, 26, 52, 52. So at each particular scale, we still have 3 anchor boxes, right? So these are 3 anchor boxes at this particular scale. These are 3 anchor boxes at this scale, and these are 3 anchor boxes at this scale. Okay. And for every particular box, you have these many parameters: 4 coordinate values, 1 objectness score, and 80 class probabilities. Now, if you consider how many boxes we are getting at the end, if you observe, we have 3 scales: 13 by 13, 26 by 26, 52 by 52. That means total number of grids at all the 3 locations combined together, we have these many grid cells. And for every grid cell, we have 3 boxes. These are anchors. So 3 anchor boxes we are having. Total number of boxes, we have 10,000 boxes. If you see the comparison between the previous versions, YOLO version 1 is hardly predicting 100 boxes. Okay, because for each grid cell it is predicting only 2, and you have only 7 by 7 grid cells. YOLO version 2, they have increased the number of grids and also the number of anchors, because of which total boxes became this. Now YOLO version 3, predictions are happening at different levels, and if you observe these 26 by 26 and 52 by 52, there are so many grid cells coming from here, and each grid cell has 3 anchors, which is giving me total this much. So if you check that way, it is almost predicting 10 times more than YOLO-V2. So even more than 10 times. Now we have seen the problem is in YOLO-V2. YOLO-V2 is actually not able to detect smaller objects. So this point I have stressed even before. Because of these kind of skip connections, if you observe these dotted lines, these are actually skip connections. Because the same information from here, it is getting propagated to this layer without any processing. So that is skip connection. Now these are having better resolutions from the input image. So input is 416 by 416. So if you have reduced to only 52 by 52, that means only 8 times, here you still have better spatial features. Now these features, if I use it in the later layers, right? So this kind of fine-grained information is very useful for predicting smaller objects. So that is what it is actually happening. So this is detection at 1 scale, 2nd scale and 3rd scale. So here better features you are propagating to this particular scale level, 52 by 52. So here you can actually detect very small objects, and here you can actually detect bigger objects, and this is for medium objects. So these are the size of objects. So because of these skip connections, these fine-grained feature information, which are actually the curves or corner locations, these kind of fine-grained features are actually preserved, and which is actually helping in detecting the objects. So this is an example of different scales. So this is bigger object. Maybe if you this is just an intuition, this might be getting predicted by 13 by 13 grid cell, predictions. This might be getting predicted by 26 by 26 feature map, and the smaller object, it is getting detected in 52 by 52. So this is just an intuition, just to show you like the smaller objects will get caught in this prediction map. Now let us look in detail about the bounding box prediction. So we saw that for bounding box, the network will output 4 values along with 1 value for objectness score. This is almost similar as YOLO version 2. If you want in very detail, you can refer to the previous YOLO version 2 videos. This is almost similar, just one minor changes here. So if you check, all these values are unbounded. Unbounded in the sense the value can be anything between -infinity to +infinity, right? If you consider, first we will try to take these two offset values. These are actually offsets. Now we need to predict the actual box values, bx, by, and bw and bh, box coordinates. So these we need to predict. If you want to calculate bx and by, we need to make use of tx and ty. Now these values are not bounded, that means it can be any value. But for bx and by, we need these values between 0 and 1 because these are normalized values with respect to the image grid cell. So these are actually with respect to the grid cell. So these are actually normalized between 0 and 1. So the output should be, input is actually +infinity to -infinity, but I need the output as 0 to 1. So what should I use here? If I use a sigmoid function, right, it will transform this into 0 to 1, right? So that is what we will do. So this is actually sigma of t of x and sigma of ty, right? These values we are getting. Now these values I will add with the top left corner cx and cy, which will give me my final values bx and by. Okay, so once I make these values between 0 and 1, I am adding that to the existing offset value. So this cx and cy are actually top left coordinates, right? That is what these equations are, cx and cy. Cx is offset from the top left of the image, okay, left of the image. Y is in the y direction, offset from the top of the image. So if you check this, these are actually cx and cy because this is the grid cell we are considering. For this grid cell, these are the offsets from the image, right? So even though we are having, if you observe here, the predictions are happening directly with respect to the image and the grid cell. These are not considering the anchor boxes. If you observe, we have the anchor boxes here, but we are not considering the anchor boxes in the XY predictions. This is what they call it as direct location prediction because it doesn't depend on the anchor boxes. Whereas width and height, W and H, whatever the bounding box width and height, these depend on anchor boxes. So if you want to calculate W and H, I need to make use of TW and TH. Now these are also actually ranging from -infinity to +infinity. And these values, my output should be only positives. So these width and height, I cannot restrict between 0 and 1 because the values can go beyond the grid level, right? So it can be 1 point something, 2 point something like that, but it cannot be negative values. So for that, the output range should be 0 to infinity, any value between 0 to infinity. Now what should I use here? If I can use exponential of then these values, it will actually convert into this much. So that is what we will do here. Exponential of TW, exponential of TH. So once we do this, then we need this with respect to anchor cell. Okay, so here these width and height are actually relative to anchor boxes. What will I do? I will actually take, let's say my anchor box is A, right? So this is anchor width and anchor height, AH and A, this one, right? So then anchor width I will multiply and anchor height I will multiply. This will give me my final bounding box width and bounding box height. So I am multiplying the anchor box's width and height with this TW and TH offset values which are getting from the network. So this is how the width and height are getting predicted. So these PW and PH are actually width and height of anchor boxes, and exponential term we are using to restrict between the positive values. Now the last value is objectness score. So we discussed in detail about this in the previous videos also. You can go there if you want to have much detailed understanding. On an overall higher level, this is how the predictions happen. TX, TY, TW, TH. These are predictions from the network. Now we are using these networks along with the anchor boxes and the offset values to get the final box prediction. Okay, so this blue box is my final box, and T naught will give me whether this particular box is consisting any object or not, how much confident it is. If this is actually 0.9, that means that this is 90% confident that there is an object in this particular blue box. So this is how the bounding box prediction happens. Now let us look at class prediction. So class prediction in YOLO-V3, they are using multi-level prediction. Previously till YOLO-V2 and YOLO-V1, in fact most of the object detectors, they use multi-class classification, where you use actually softmax activation function. Your output will be, you will actually consider the maximum confidence score label, the label which is having the maximum confidence score, and that is your final class, because generally the output will be confidence score values ranging from 0 to 1. But what is multi-label classification? So if you want to check multi-label classification, this is a single image. This particular same thing has multiple labels. We can say that it is a person, and she is a woman, she is an artist, it is actually a human body, she is a dancer, right? So there are so many labels. You can see the examples here. From the single image, you can actually predict so many things. Okay, so this is actually multi-level prediction. Now in YOLO-V3, they wanted to do this multi-level prediction. So this indicates that for single bounding box, for each bounding box, you are predicting multiple labels. Then how can we do this? First of all, if you are getting confidence scores between 0 and 1, and if you are using softmax, then sum of all your confidence scores will be equal to 1, right? And you will generally take the maximum of confidence score, whatever the maximum, that particular argument, argmax will give the location of that, label ID of that one. So this is what you generally do for taking the label value. Now if you want to do multi-labels, you want to consider other labels also, then how can we do this? Here by this particular softmax activation, you will only get one particular value at a time. So this is an example. If you check this, binary you can ignore, this is only just two classes, so only this much. Multi-class, usually if you check, the sum of these values will be equal to 1. And usually what is the class here? We'll consider the maximum probability score. So if I give this image to the classifier, my output will come as dog, because whatever the classification score is there, the highest value, we will take only that prediction. Now multi-label, if you check here the example, it is giving 0.8, okay, and it is giving 0.7, high confidence score for this also, plant, right? So these two are coming as predictions, dog and plant. But here if you observe, the sum of all these confidence scores is not equal to 1. Is it equal to 1? No. 0.8, 0.7, it is 1.5, right? It is not equal to 1. How is this possible? If you want to do it that way, then what you have to do is, you actually, in this case, you are using softmax, right? If you want to do this multi-label, you remove softmax and you use sigmoid. You use sigmoid activation function for every node here, for every label here. See, inherently in the network, these are nothing but the nodes, right? Prediction nodes. So for each prediction node, you actually use sigmoid instead of softmax. Now sigmoid will only make sure that it is between 0 and 1. It doesn't matter if it is higher value or smaller value, it don't know, right? Because it is independent of these predictions. It will only take care of this one. This particular one, it will only think of plant. It doesn't bother about all the other things. So that is how actually you can do multi-label prediction. So multi-label prediction means you are using the sigmoid classifiers. This another name is actually logistic function, right? So usually in papers you will see this term, logistic classifiers. So you will use independent logistic classifiers. If you are training on COCO dataset of 80 classes, that means you have 80 classifiers, independent classifiers you are training. everyone is a logistic classifier, each one of them. And accordingly, we need to use binary cross entropy loss. The loss function in case of sigmoid, it is actually categorical cross entropy, whereas in case of logistic, you need to use binary cross entropy. So the loss function also you will modify accordingly. So this is how the class prediction happens in YOLO-V3. And let us look at the loss function difference while we are talking about the loss anyway. So we will look at the loss function, how it looks like. This is the loss function for YOLO version 1 and version 2. If you check, all of the terms are square root terms, right? Square root error. This is the prediction. I mean, this is the ground truth and this is the prediction. This is the ground truth, this is the prediction. So all these terms are square root error terms. Same thing for objectness also. So for objectness score, this is the target value, this is the predicted value. Target value, predicted value. Same thing for classification loss also. If you have 10 classes, so for all the classes you take actual value, predicted value. Everything is square root loss. But in case of YOLO-V3, one change is they are using the classifiers here, right? So if you are using classifiers here, this cannot be square root loss. This should be entropy loss. At the same time, this also you can change it into entropy loss, because these are probability scores. These are not some random values, right? If these are probability scores, then entropy loss will give better convergence compared to square root error losses. So the modifications they have made to loss function is they replaced the confidence loss, which is objectness loss, and classification loss from square root errors to cross entropy loss functions. I mean entropy loss functions. So this is just a representation purpose. I actually took the entropy loss function values and I kept it here just to give you a feel of how the loss function looks like in the end in YOLO-V3. They haven't actually provided the loss function in the paper. So but I am assuming that if you are keeping the entropy loss functions, then these are how the loss functions looks like for confidence score and the classification. So these are actually log functions. So you can see this is how you can see these are entropy loss functions. The main point you should take is the confidence scores and the class probabilities are not using square root errors anymore. They are actually using the entropy loss functions. Right? So these are all about the YOLO-V3. So far we have seen the architecture changes, which is the backbone change, and also the changes in the detector part where you have skip connections and detections at multiple scales. And we have seen how actually the prediction happens, which is almost similar to YOLO-V2, the anchor boxes and then the relative terms of offsets calculation. So all these are actually similar to YOLO-V2. So we just looked at that. Along with that, there is one change with the class prediction. Here multi-label classification they started including. So that is one thing we saw, and couple of changes in the loss functions. Now we will see the performance of the model. So as we have mentioned earlier, this is only an incremental improvement. The others did not make any too much of significant improvement in the model per se. They just added few more layers to the backbone and couple of skip connection and leaky ReLU, these kind of improvements they took from the previous papers. YOLO version 3, if you consider only MAP value, then it is still not the state of the art. If you check 33 MAP and RetinaNet is actually 38, almost 37.8. So it is still not the state of the art, but if you consider the time taken, it is 50 milliseconds, and here RetinaNet is taking 200 milliseconds, almost 4 times faster than RetinaNet, right? And hardly 4 MAP difference. And it is almost comparable to this one SSD also, SSD 33, right? And if compared to SSD, it is 3 times faster, right? So it is still the fastest YOLO model, but it is still not the state of the art model. Okay. So this is all about YOLO version 3. So finally, as a conclusion, you can say it is a very good object detector. It is most suitable for most of the applications as it is much faster and it is an accurate model. It might not be the state of the art in terms of accuracy, but it is definitely the fastest object detector at that time. Thank you. In the next video, we will look at the next version, YOLO version 4, which is a big jump compared to YOLO-V3.